Hello everyone, I am Shubham Kumar Singh and I have been studying about transformers for last 10 to 12 days around. It has been fascinating. I have learned a lot. In the process, just to understand, I ended up implementing transformers from scratch in my repo. We'll not go over the repo today. I also produced a few blogs that I'll publish soon, in which those are mostly my study notes, which took the form of a blog. In this video, what I wanted to do is I wanted to cover the paper Attention is All You Need, the paper from where it all started. Yeah, this paper. So let's go over this paper and try to understand what happened. Why is transformer such an important thing? So to understand transformers, you'll have to go a little back before what happened before transformers. So before transformers, we used to had something called RNNs. RNNs. And RNNs were like this. Symbol neural networks in which we feed word by word, token by token. Every token is processed at a time, and the result is processed. Result is outputted by this part. There are two parts: encoder and decoder. Now there are obviously a lot of issues with this encoder. Main issue being, if you look at, yeah, this is a very awesome blog which you see on your screen right now. I recommend everyone to read this blog. So the main issue with this entire process is that if we, let's say our sentence is very long or we have whole paragraph, only one context vector will be passed to the decoder. Now, how can just one context vector carry the meaning of all these tokens? Let's imagine there are 1000 tokens and I have to fit the context in one context vector. So that's of course a bottleneck. This bottleneck was handled by something called attention. Attention was introduced before transformers. What attention says is कि instead of passing this one context vector, pass the output of all the encoders. Take the output of all the encoders, stack them up, and pass them one vector and pass them to the decoder. That is what the idea of attention is. That is a very good idea that did very well. So now this paper comes. Attention is all you need. So this paper says that let go of the encoder, let go of this R and N recurrent systems. We'll just keep attention. That's all, and that's why attention is all you need. And this paper introduced a novel architecture, new architecture, and that architecture worked super well. Why it worked super well? What was the architecture? We'll look into this. So this is where they're saying there is no need recurrent neural networks, long short-term memory, and gated networks in particular have been firmly established the state-of-the-art approaches in sequence modeling, such as language modeling. But unme the boundary is again the bottleneck of the context vector. That is all they explain here. Now they are introducing a new architecture. This is the architecture which they introduced. So what it might look a little bit scary at first, but believe me, it's super simple once you get to know what is happening. So imagine like there are two parts of it, right? Of course. See, there are two parts of this model. First part is this. This is encoder. Okay. This is decoder. Cool. In encoder, there are two layers. Second is feed forward, and this first is attention layer. So if you see attention layer comes here, here, and here, three places. Attention layer comes in three places in the transformer architecture. It's a little different everywhere. I'll cover attention in a separate video. You can watch that video because attention in itself is a huge topic and very interesting. I think you should definitely learn. I'll cover attention in a separate topic, and I will also publish a separate blog just to cover attention, understanding what is attention, intuition behind it, and how to implement it. Actually, I already have published a blog. If you want, you can read this blog. It's on my Medium. I'll link in the description. Understanding attention in transformers with code. So you can just go through it to understand attention and what happens. I'll cover it in a separate video. Let's come back to transformer. So the architecture is we have 6 encoder blocks. This NX is 6. 6 encoder blocks stacked on top of each other, and then 6 decoder blocks stacked on top of each other. We pass the input, this input, into the encoder blocks. But before that, of course, we convert input into embeddings and we add something called positional embeddings, right? So the beauty here is, unlike RNNs, let's say I have a sentence. Let's say the sentence is uh, I like transformers. All the words will be all the words will be fed into the transformer parallelly, just like this awesome blog tells us. If you see here, all the words are going in parallelly, unlike RNN. So this parallelism is what makes transformers awesome, right? So this parallelism, if you see all the words are going in parallelly, that is how it goes inside this input. Now, for all these words, we convert them into embeddings first, and then we add positional embeddings. What are positional embeddings? Now, since these words are going all at a time, we need some way to tell the transformer which comes later and which comes first. The position matters a lot. Let's say I say uh, Shubham eats Shubham eats an apple, right? That is a sentence. If I reverse the position, apple eats Shubham, the meaning is changed entirely just by changing the position. The words are the same. So position is very important in context. So we need some way to give the transform idea that what position it is. So position ka idea we try to give idea of position by something called position embeddings. So let me refer to this repo. Okay, this is the repo which I'm making using to implement transformers from scratch. So if you see in this repo, I have made this visualization. You can see the file visualization position embeddings if you want to know how I visualize it. So basically it's very straightforward. I have stacked position vectors on the top of each other. So every position will have a different position vector. First position will have a different position vector. Second position will have a different position vector. I have stacked from 0 to 500 something. And you can see first position vector looks something like this. Then second, then third. All these are stacked on the top of each other. These values are 1 and 0. So now we'll add these position vectors into our original vectors. The word vectors, these vectors basically. For example, any word any word is converted into embedding is a positional vector, and then we input this into the encoder block. Encoder does its work. It passes through multi-head attention, then it passes through feed forward, then additional, and then they add and normalize, and then they give it to the decoder. Right? So this is the basic architecture. The decoder does this processing, and finally, when the decoder is done, we have a linear layer which takes this output from the decoder and scales it up to the size of the vocabulary, whatever the output vocabulary is. Our vocabulary is nothing but a set of words in the output language. For example, if we're translating from English to French, this linear and French, let's assume French is 10 lakh words, right? So this linear layer will convert whatever dimension is into 10 lakh size vector so that we know what word we're talking about. And then softmax will just turn it into probability sizes. Whatever the maximum probabilities, will take that up. And that is how probabilities come out. ठीक है, position headings we embed here also. One more thing, what is this output embedding doing here? Imagine you're training a transformer. Let's say we are converting from English to German, French, English, Hindi, whatever. You'll feed the English sentence here, and while training, you'll feed that full sentence in the target language here in this output. Full sentence in the target language already. Right? Let's move forward. There are many more details which we'll discuss later. So here I already talked about the encoder is comprised of n equal to 6 identical layers, and then D model. What is D model? D model is basically the dimensions of these embeddings. D model is constant. Why? Because one very important thing in a transformer is residual connections. Don't forget. So every layer has a residual connection. You see coming from here. This is a residual connection. This is a residual connection. So we have a residual stream going on. In that stream, we are adding the results from all the layers, right? So basically, after every layer, like there are n equal to 6 blocks. After every layer, the final result is the original input plus, in addition to the outputs of all the layers before it. That is why we need this residual stream. It's super important. Okay. Moving forward, then we have decoder n equals to 6 decoders. That's pretty much it. Attention scale dot product attention they're using. This is the formula of attention. What are Q, K, and V? Q, K, and V are query, key, and vector, which is for every token. We'll calculate its own query, key, and value vector, and then we'll try to flow some information around each other. Again, this is very interesting attention topic. Just assume that somehow the information is flowing and we get some goodness. We'll discuss later how attention works. And then we have multi-headed attention. So basically, if one attention layer is doing something, we have here 8 attention layers parallel to each other, not sequential. So the encoders are stacked sequentially, one on the top of each other, while heads are placed parallelly. So token comes in every attention layer, independent calculations are happening. We combine those calculations and then we go to the encoder block. In that encoder block also we have 8 parallel attention layers. All of them are so attention, what attention does essentially is learn patterns and try to learn what is the relation of this token with other tokens. So there can be multiple relations: pronoun, noun, pronoun, part of a phrase, sentence, everything. So every attention head tries to learn different things. We use 8 attention heads as per this paper. Okay, and this is, they have defined how to combine the results from those attention heads, which is very straightforward. You just take all the results from the 8 attention heads, concatenate it into one big chunk, and then linearly scale it to whatever desired output or size you want, using a simple n dot linear. Okay, these are all WQ and WK. These are all parameters of this layer which are learned during training. Now they are telling that they have 3 types of attentions going on. One is type is an encoder, then 2 types in decoder, which we just saw here in this model. So first attention layer is, I'll just, can I move this? Yeah. So first type is here. This is number 1 type, plain vanilla attention, some say simple. Then we have here, this is masked self-attention. Masked self-attention, why is masked? So what is masking? Refer to that blog. Why masking, I'll tell you. So when I'm training my transformer, I'm feeding all the entire sentence, right, into this encoder. But that is not the reality, right? When we'll use this transformer during inference, it will not know the entire sentence. It will be predicting word by word. So when it's trying to predict some word, it will not be able to see what are the next words, right? So that is something. So that is why masking exists too. But encoder will always know the entire sentence, right? It will always know the entire sentence. So to simulate training conditions, we add something called a mask. So mask is nothing. For every word, we don't allow the transformer to look ahead and learn behave like an inference thing. Now this is the third type of attention. Here in this attention, we use inputs from encoder as well. This is how cross language attention happens. For example, English I am Shubham corresponds to मैं शुभम हूँ in Hindi, right? So I in English will correspond to मैं in Hindi. That is something transformer will learn in this layer. So we are getting inputs from encoder, the original, as well as from here, the target. From here, Hindi is coming, मैं शुभम हूँ, and from here, processed English is coming, I am Shubham. And multi-head attention is learning that what is the connection between those two words. So that's why we need this multi-head cross attention. This is called cross attention. This is called mask attention. This is called just attention. Cool. So we have 3 types of attention. Again, I'll discuss in detail in next video. Coming to positional embeddings, you already covered this. This is the very complicated formula of positional embeddings, but I showed you how they look. Feel free to look into that code. Okay, this thing. Position-wise feed-forward networks. In every encoder and decoder you see here, this blue block. After attention blocks, we have a feed-forward network. Imagine the attention blocks where information is being exchanged among tokens, and then this neural network where every token is being processed and refined more, every token, right? So that is how you can imagine. So we definitely have feed forward. What happens in feed forward is this multi-head outputs has the output of dimension 512, and then we scale it 4 times within attention, and then we descale it to 512. So 512 is scaled to 2048 and then back to 512. I think they would have mentioned here in position. Yeah. So D model is 500. So if you see, there are 2 layers. We are scaling and then we are downscaling. So from D model is 512, middle layer is 2048, and then we scale it back to 512 so that we can pass it to the second encoder. So one thing to notice, every layer has an output of 512. From here, embedding's dimension is 512, d underscore model. We give it 512, then it will output. Every layer's output is just 512. Why? So that we can add residual connections at any point in time. It's very straightforward. If you want to just add a linear layer to scale it to 512, nothing. Okay, then we have an embedding and softmax. What embedding and softmax are doing? This is our embedding layer here. Embeddings are learned during training, right? And then we have a softmax here. Softmax is to convert this into probabilities. This is a linear layer, it will output, and we just want probability distribution. That's very straightforward use of softmax. Okay, then why self-attention? I think we have covered it. Yeah. So this model achieved state-of-the-art results in English to German and English to French translation. So that is something very awesome. It was trained on 8 NVIDIA P100 GPUs, which is a very small training duration as per our small infrastructure and duration as per today's standards of GPT-3, 4.0, Claude 3.5 and all. Cool. Yeah, this optimize is something very interesting. So they are using Adam optimizer, which is again very obvious choice. But their learning rate is something very complicated. So this formula is very hard to make sense. So I added a visualization in my repo. Let me see if I can find it. Where is my repository? Yeah. So for this, these are the code. We'll discuss code in the next video. This video will already. So this is the custom learning rate schedule. What they're saying is for warm-up, for some number of steps, they call it warm-up steps, we'll increase linearly. We'll increase the learning rate linearly, then we'll decrease it. Okay? Inversely proportional to, the decrease is inversely proportional to the number of steps. So you see, the decay starts from here. Okay, so that is a little complicated. That helps a lot, and I think that is pretty intuitive how that will help, because from here we are decaying, and from here, we know for warm-up steps we are not going to reach our local minima. So let's just keep on increasing, and once warm-up steps are done, let's start the decay. So that is what they're doing in this difficult looking formula. That is pretty much straightforward. Let's move forward in a paper. Regularization mein they are using dropout, standard dropout. Dropout is used inside attention layer as well, and dropout is also used while. So dropout is also used when we are doing this residual connection. So if you see here in this residual, yeah, can I clear this please? Thank you. So this layer, when this layer is going inside, we see we are adding and normalizing. So this adding and normalizing also contains a step of dropout, which is not mentioned here. Okay, in the repo, in the code, I will show you where I have used dropout as per the paper. Cool. Dropout is just a regulation technique, and then we have label smoothing as well. What is label smoothing? It's very straightforward. So wherever we are using one hot encoded vector, what we'll do is instead of having one word as 1 and all else is 0, we'll make that 1 as 0.9 and then distribute 0.1 uniformly across all other indexes. Results were state of the art, and this table, I want you to go through this table. This table just states that this is ablation studies. They were trying to learn what works best. And this table in general shows that bigger model performs better, which we obviously know today that bigger models perform better. This table also answers that how they decided the number of heads will be 8. So if you see, when they're increasing the number of heads, the blue score is increasing, but at 32 it starts to decrease. So at number of heads equal to 8 and 16, the score is almost the same. So I think they chose to stuck with h equal to 8. So they're playing with all of the parameters. You can look at it, what are the results of the transformer. But the bigger transformer, the better. If you see, this is a big ass transformer and it produces the best results, which is like very common knowledge today. And yeah, so this is the paper. I know I have a lot of explanations are very hand wavy, but I hope this summarizes a little bit. We'll cover the implementation and deep dive into attention in separate videos. I think that's pretty much it. If you have any questions, feel free to hit me up. You have a repo, and we have, yeah, thank you guys, thank you so much.